Good morning, ladies and gentlemen. Today we are starting the next part of our lesson on electric fields. And we're first going to talk about how electric fields helped Robert Millikan discover the exact charge of an electron. And the way he did it was very cool, because he basically took some oil drops and started putting them through an electric field and had them start falling until they stopped and floated in midair. And using that, he's able to determine the charge of an electron. Let's take a closer look.
Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they...
Let me pause it for a moment here. You notice there's a positive charge on the top plate and a negative charge on the bottom. So right now, inside this diagram, there's a very strong electric field, okay, which Robert Millikan was able to control the strength of.
Strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise.
And basically now in this diagram here, we understand that there's weight pulling down on the oil droplet, and there's QE pulling up on the oil droplet. And when the oil drops, when he fine-tuned the electric field to a certain strength, he noticed that he could get these to perfectly balance. So of course, if there are two charges on an oil droplet, as in this example over here, that means that doubles the strength of QE. So while certain oil droplets are able to stay perfectly still, hanging suspended in midair, other oil droplets will start to move upwards.
Depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Okay. So this is just a quick version of the same exact thing, but basically when there's a small electric force on, the droplets slow down. When you turn the electric field on even stronger, the oil droplets would just fall and eventually hang in midair. Okay. Now, move this up for a moment. Okay, so just to recap. He was able to identify the mass of a single oil droplet. And notice this is different than the previous problem before with the projectile motion in the last video. In the last video, we were only talking about a single electron being shot through. And with a single electron, the mass is so small that the weight is so tiny that it didn't really matter. In this case over here, the oil droplet has a much larger mass. It's not going anywhere. It's just, in this case, it's hanging perfectly suspended. So we end up with the Fe equals to Fg. The electrostatic force is equal to the gravitational force, or basically the QE is equal to mg. So now we do a quick practice question with this. Oh, I just noticed over here that was a mistake, so I should say newtons. But we'll do question 4. An oil drop weighs 1.9 times 10 to the negative 14 newtons, is suspended in an electric field of intensity 4 times 10 to the 4th newtons per coulomb. So just to draw that out, I have my oil droplet, I have mg, which is equal to 1.9 times 10 to the negative 14 newtons. Point up is QE. So over here, we know the strength of the electric field. What's the exact charge? So knowing that QE can be set equal to mg, Q is equal to 1.9 times 10 to negative 14 newtons divided by 4 times 10 to the 4th newtons per coulomb. And this equals to 4.75 times 10 to negative 19 coulombs, which is approximation. Now, the follow-up question is, how many electrons are actually within this charge? Well, we know the charge of one electron is 1.6 times 10 to negative 19 coulombs. So if we divide this, or we even set up a proportion, we have 4.75 times 10 to negative 19 coulombs. I know that one electron is 1.6 times 10 to negative 19 coulombs. So dividing it out, I can see that this total charge is equal to approximately 3 electrons. Okay? And basically, when Robert Millikan did his experiment, he did it hundreds and hundreds of times. He found that every charge was always a multiple of 1.6 times 10 to negative 19 coulombs, and that there was never a charge smaller than 1.6 times 10 to negative 19 coulombs, which he then therefore inferred that the charge of an electron has to be 1.6 times 10 to negative 19 coulombs. Okay. The next portion we're going to talk about is about the electric field created by point charges themselves. Just similar to how the Earth creates its own gravitational field, we're going to be talking about how electric charges are going to be creating their own electric field in this case. So let me just bring this back to gravitational force for a moment. If you remember for gravitational force, I'll actually do this on the whiteboard over here. Fg was equal to mg, which we could also set equal to g, mass of the Earth, mass of the person, over r squared. And when we set the two formulas for weight or gravitational force equal to each other, we could cancel out the mass. So let me just draw this. Here's the Earth, here's the person, we have the little mass, we have the big mass. Now the little mass cancels out, meaning that I'm able to solve for the gravitational field of the Earth itself using g equals to the universal gravitational constant times the mass of the Earth divided by the radius of the Earth squared. And that solves for the gravitational field of Earth. It has nothing to do with the person standing on the Earth, but any person that's placed within this gravitational field will automatically feel a force. Okay? Now the same idea applies to point charges. I know that my original formula for Fe is equal to Q naught E. Q naught is a tiny little charge that exists within an electric field. But my original formula for electrostatic force was this force between two charges, K Q1. Let me actually rewrite that a little bit. K Q1 Q2 over R squared. Now in this case over here, I might have some sort of large charge of Q. Let's say this one's positive. And it's creating its own electric field. If I take a tiny little positive charge of Q naught, then it's going to be that Q naught, that tiny little test charge that's placed within, will feel, of course, an electrostatic force within this field. So just like the Earth and the person, that tiny little test charge can cancel out when I set the two formulas equal to each other, which leaves me the formula: the electric field of the charge is equal to K times the large charge producing the electric field divided by R squared, or however far you are away from the center. Okay. So that's how we derive the formula. So in this case over here, if I want to solve for the strength of electric field, E is equal to K Q over R squared. Okay, and this applies to point charges, meaning single points with a tiny points, but as well as hollow or solid conductors. What do I mean by that? Over here, just as with before our picture of the Earth, okay, all distances are measured from the center of the Earth. Okay, so it doesn't matter how large it is. So in this case over here, if I wanted to solve for the electric field at a certain point, I would measure it from the center. Even though I know that everywhere inside the hollow conductor, E is equal to 0, when I use the formula E equals to K Q over R squared, I still measure from the center of the solid or hollow conductor. Okay. So let's do a quick practice question with this now. Calculate the magnitude and direction of the electric field at a point P 30 centimeters to the right of a point charge Q, which has a value of -3 microcoulombs. Okay. So micro, of course, means times 10 to the -6 coulombs. So if I want to solve for the electric field, E is equal to K Q over R squared. Again, note I do not include charge sign into my equation. So this would equal to 9 times 10 to the 9th newtons meter squared over coulomb squared times 3 times 10 to the -6 coulombs divided by 0.3 meters squared, which equals 3 times 10 to the 5th newtons per coulomb. But what is the actual direction of that electric field at point P? Here's point P. I know that if this is a negative charge, the electric field goes into negative. That means at that point, it should be pointing left into the negative charge. If you were to flip the charge instead and have a charge of +3 microcoulombs, well, if it was to be positive, that means it would be going out of positive. So instead of going to the left, the answer would be to the right. Okay? Now, please note, is there actually anything at point P? No. It's just an empty point of space next to the charge. Just like with the Earth, if there was nothing on the surface of the Earth, you would still have the gravitational field, even if there is no mass at all to feel that weight. Now for our next question, let's take a look at question 4. It starts off the same. Part A asks, determine the electric field 0.1 meters from a point charge Q. Okay, that carries a charge of 0.2 microcoulombs. So we have a point charge Q1, 0.2 microcoulombs. They want to know what is the electric field 0.1 meters away. I didn't specify. We'll just assume 0.1 meters to the right. Okay. So at this random point in space, they want to know what's E. So E, of course, is equal to K Q over R squared, 9 times 10 to the 9th, 0.2 times 10 to the -6, divided by 0.1 meters squared. you end up with 1.8 times 10 to the 5th newtons per coulomb. Now, because it is a positive touch charge, we know electric field lines go out of positive. We know that the direction of this is going to be to the right. Okay, so 1.8 times 10 to the 5th newtons per coulomb. Now, the thing is, they're going to take a second charge and place it at that point now. So just like when you put a mass inside the gravitational field, it feels a force of mg, okay? So just like a mass that's placed inside a gravitational force, that mass will feel a force of mg. In this case, when you place a charge inside that electric field, is going to feel a force of QE. So in this case, we're going to put a second charge now at location P. That second charge has a value of 0.8 microcoulombs. Now, if I want to figure out the force, Fe is equal to QE. So in this case, Q is the charge that's feeling that force. That's going to be the 0.8 times 10 to the negative 6 coulombs times 1.8 times 10 to the 5th newtons per coulomb, 0.144 newtons. In this case, because they're both positive, and because positive charges feel a force in the same direction as the electric field, it's going to be to the right. Okay. Now, notice we could have, if we had wanted to, we could have used the formula Fe equals to K Q1 Q2 over R squared. That will solve for the total electric force as well. Just like when you go to this example over here, if I really want to solve for the force between the person and the earth, I could have used Fg equals to G M1 M2 over R squared. I'll use the mass of the person times the mass of the earth divided by the radius of the earth squared. But it's tedious. If I happen to have the gravitational field already, if I happen to have the value of G, it's much easier to just use mg. And just like with the charges, okay, if I happen to have the value of E already, rather than using K Q1 Q2 over R squared, I could simply use QE. Especially since we're going to be dealing with slightly more complicated questions now. Okay. Let's see. Now, what happens if you have multiple point charges creating an electric field? Okay. In this case, we have one positive charge and we have one negative charge. And as I had said yesterday, electric field lines always, of course, go out of positive and into negative. And we can see, if we just to trace out the arrows, they go out of positive and into negative. But I need you to understand, this diagram is really a diagram of the sum of the electric field vector components. What exactly does that mean, though? Let's pick any point. Let's say we take this point over here. We know that the electric field of the positive charge always goes out of positive. So since it's always going out of positive, at that point, E1 is going upright. The negative charge, electric fields always go into negative. So it's going in that direction. E2 is down and to the right. If I were to figure out what's the vector resultant of the top right, and the bottom right vector, the total electric field would be to the right, okay? Which is what our diagram shows. Right here we have an arrow going to the right. It's the vector sum of the two electric fields. However, you're going to need to be able to calculate each of the components and solve for that vector sum. Even if I pick a point as over here, okay, I know that it's going out of positive with a very strong electric field because it's closer to the positive charge. At the same time, it's going to be going in towards the negative charge. But the electric field isn't as strong because it's further away. But as a vector sum, you see this arrow over here, it points in this direction. So sigma E. So every point is going to be a vector sum of the two electric fields that are being created. And right now our job is to figure out what's the total based on the location. If it happens to be somewhere over here, that's easy because it goes out of positive, there's E1, and it goes into negative, there's E2. You simply add up E1 plus E2. Okay? Even if I pick the point over here, it goes out of positive, there's E1, it goes into that negative charge over there, there's E2. But of course, E2 is going to be a lot weaker than E1. So in this case, I would subtract the two E's to solve for the total vector component. Okay. Now, I must make it clear, do not get confused between electrostatic force and electric fields. Okay? Before I do this question, let's look at an example I spoke about yesterday about the Earth and the Moon. Okay? If I wanted to solve for the gravitational force between those two planets, this would be M1, M2. I would do Fg equals to G, M1, M2 over R squared. And R, of course, would be the total distance between the planets. However, if I wanted to solve for the gravitational field in between those planets, I want to know what's the total gravitational field at that location. This is not the right formula to use. Now, there's nothing that actually exists at that location, but I know that it is a certain distance away from the Earth, as well as a certain distance away from the Moon. So in this case over here, I know that the first gravity 1 points towards the Earth, gravity 2 points towards the Moon. So I would have to solve for the gravitational field of the Earth, which would be G1 equals to G M1 over R1 squared. And I would subtract that from G2, which is equal to G M2 over R2 squared, because they're pointing in opposite direction. Okay? And once I know what the total gravitational force is at that location, once I know what the total gravitational field is at that location, if I were to put a little astronaut over there, in between, we could solve for his overall mg based on the combined gravitational field. And it's the same way with charges. Okay? Right now, we have 2 point charges separated by a distance of 10 centimeters. One has a charge of negative 25 microcoulombs, and the other one is 50 microcoulombs. So we know that at this location, E1 will go towards the negative charge. At the second location, because the second charge is positive, is going to go into that. So that would be E2. So in the end, if I want to figure out what the total electric field is, I have to solve for E1, then E2, and add them together. So in this case, E1, which is based on negative 25 microcoulombs, is equal to 9 times 10 to the 9th newton meter squared over coulomb squared times 25 times 10 to the negative 6 coulombs divided by 0.02 meters squared. 5.625 times 10 to the 8th newtons per coulomb left. E2 will equal to 9 times 10 to the 9th newton meters squared over coulomb squared times 50 times 10 to the negative 6 coulombs divided by 0.08 meters squared. In this case, will equal to 7.03 times 10 to the 7th newtons per coulomb left. So the total electric field would equal to 6.33 times 10 to the 8th newtons per coulomb left. Okay, so that's the sum of the two electric fields. Now, if I were to put an electron in that location, I know it's going to be attracted to the attracted to the positive charge, repelled by the negative charge. It's going to feel a force to the right, and that force would equal to 1.013 times 10 to the negative 10 newtons, right. So in this case, there are two parts, solving for the total electric field and then solving for the force on a charge placed inside the electric field.